Well, ladies and gentlemen, chemistry students, welcome. Today's show is going to be about light, and of course, I am in trouble with my pen color today. There we go, and there it is. So today, we'll discuss light in all its generalities. You have a reading guide to work over and one assignment, and the example for the assignment is after this is attached to this lecture as well. So, what is light? For one thing, what we know is light. If we look at a spectrum, we have visible light, and it's only a smaller part of this whole world of light. These are called electromagnetic waves. Electromagnetic waves, and that's what light is. It's just a wave, and we'll talk about that later, and it has various wavelengths. These wavelengths are in nanometers, which is times 10 to the minus 9 meters. That's a nanometer. And you notice that what we can see is a very small part of this whole spectrum. Gamma rays has the shortest wavelength, 1 times 10 to the minus 14, around there. And then we have X-rays. Then we go to ultraviolet rays, and then that little part here is visible. Then we have infrared. Then the radar frequencies, FM, TV, shortwave radio, and then AM, amplitude modification and frequency modulation. And here are the wavelengths. As we go from left to right, the wavelength gets larger. And wavelength for us is going to just be this little simple lambda. This is called the wavelength. So as we go from left to right, it gets longer. And we'll show you a relationship with energy. As we go from right to left, energy gets higher. Or this is low energy on this side, and this is high energy on this side. I'll write energy down and low energy. Now this is important because let's look at this. We always talk about energy and how things with high energy, all these things from this part of ultraviolet over has a tendency to break bonds, cause damage. X-rays, again, even though it passes through human tissue fairly well, it can interact with some of the cellular structure to cause damage. And gamma rays definitely causes damage. So we got all these different type of things. If we go to infrared, this is heat, what we call heat to this part. And then as we go longer wavelengths, it gets less dangerous till we get to AM and shortwave. So this is what we call the electromagnetic wave on the spectrum. And you don't know the spectrum: red, orange, yellow, green, blue, indigo, violet. There's no such thing as purple. Even though this is purple, this is actually a shade of blue. So when we talk about light, we talk about light as a wave and as a particle. We have this duality. Duality, meaning that it can exist both as a particle and a wave. It does both. Einstein, when we'll talk about this later, proved that light acts as a particle. And then as a wave, we're talking about classical physics, where we can reflect light, diffract light, refract. And we'll do more on wave mechanics in physics. But for right now, we're going to focus on light as a wave in this part of our lecture. And the reason why is that electrons that we're going to be talking about interact with light. And as a wave, light has electrical and magnetic components. So we usually draw it like here's our wavelength, and we have the magnetic version as perpendicular. So this is electrical. Sorry, it keeps doing that. Electrical and going, and this is magnetic. And why is my pen doing this? All right. So we've got both. And a wave has wavelength and amplitude. So let me look at this drawing of a wave. Just look at one side. From here, this is 0 to the highest point is the amplitude. Wavelength is from peak to peak. And we have, and we're going to be using these two equations, and we're going to cover this later. E is equal to h nu, where E is energy, and C is equal to nu lambda, and nu is the frequency. And we'll talk about that in a minute. And actually, here it is. The equation we want to use, C. C is the speed of light. When we talk about the speed of light, this is how light in a vacuum. And it's 2.99 times 10 to the 8th. And so this is this equation here. This is the wavelength. Now, in chemistry, since we use a lot of variables, a lot of constants, you guys need to know what each of these mean. Nu is what we call frequency. How many times per second something goes by? How many peaks do we see? Wavelength is the length. So this is called meters. So C, speed of light, is equal to lambda, the wavelength, times the frequency. The wavelength must be in meters. Frequency must be in 1 over seconds or hertz. Both of those are the same thing. This is important. You got to have the numbers in those units, or you're going to get the wrong answer. All right? H, you have this number, 6.626 times 10 to the minus 34. This is Planck's constant. And this is one of these constants that we always use in science, and the unit is joules times second. And when we're talking about energy, and Planck divides this, all energy of a light beam is equal to this constant times the frequency, which is nu. And so E is equal to energy, and you got everything else is given to you. And that's what we have to do. And so the calculation is going to be easy. It's going to be, I have two examples here. We want the energy of the wave that has a frequency of 5.4 times 10 to the 20th. And then the frequency, and we're just going to do this one right now. So we're looking for the energy that has a frequency of 5.4 times 10 to the 20. So nu is 5.4 times 10 to the 20th hertz, or per second. And we want to know what the energy is. Well, the energy is equal to this. We want this. This is given to us. So E is equal to 6.626 times 10 to the minus, let me go back up here to my constants, that's 34, times 5.4 times 10 to the 20th. And then we're going to have our energy. The unit is going to be joules, because if we do the unit analysis, this is going to be joules times second times 1 over second. The seconds cancel, and we'll have joules left. Get my handy dandy calculator out. My cat is helping. 6.626 raised to the minus 34 times 5.4 raised to the 20th. And we should get a number of 3.58 times 10 to the minus 13th. And that is the answer we're looking for. You need to start using scientific notation, guys, and we'll talk about this on Tuesday. And I'm going to do one more example. Energy of a wave that has a wavelength of 3.7 times 10 to the 3 meters. we're going to be doing two things. We're going to do the stepwise. C is equal to H nu. No, C is equal to lambda nu. We'll convert that. We're looking for the nu. So we'll divide both sides by lambda. So nu, and I'll move the V over. C over lambda. You guys can work this out. And then we're going to use E is equal to H nu to figure out the energy. So also what you can do is combine these two, substitute together. So E is equal to H C over lambda. And that's another equation you may want to see. So I'm going to use this equation, but you can use either both of these or this one. It doesn't matter, you're going to get the same equation. 6.626 raised to the negative 34 times 2.99 raised to the 8. Then divide by 3.7 raised to the third. You're going to get a number that is equal to 5.35 times 10 to the minus 29th, and that's joules. Believe it or not, that is a low number for energy, but it is equivalent to what this wavelength is. And that is the end of the lecture. Thank you guys, and have a nice day.